As we continue on in section 2.2, the three objectives we're going to address in these notes are continue to use table A to find the percentile from the normal distribution. I will reiterate solving the normal distribution using the calculator, and then we'll use the normal distribution to determine the z-score. Basically, we're going to go backwards, and we looked at a little bit at that yesterday. Really, the only new thing that we're addressing in this part of the notes is that you have to be more formal now in how you solve these problems. In the book, they will use this indicator of the 4-step, which means do your state, plan, do, and conclude. In chapter 1, when solving statistical problems, we had our own state, plan, do, and conclude. This has its own too. They are somewhat similar though. So jot this down in your notes. You're going to have this section on the first part of day 4. And what you want to do this time, when you solve any type of problem using the normal distribution, first thing you want to do is state, which means express the problem in terms of the observed variable. And I'm going to show you a couple of examples where I do the state, plan, do, and conclude. The plan is draw a picture of the distribution and shade the area of interest, which we talked about yesterday. The do is actually perform the calculations. Either standardize your x value to find the z-score and then use table A to do finding the area or to go backwards. And the last thing you want to do is just conclude the problem by answering it in the context. Now in the problems we looked at yesterday, we found areas under the curve given various z-scores. Today we're going to have the real life problems. And the only thing different is this time we have to find the z-scores ourselves and then do exactly what we did yesterday. So let's just take a look at this example here. When Tiger Woods hits his driver, the distance the ball travels can be described as a normal distribution with a mean of 304 and a standard deviation of 8 in terms of yards. That's how I'm interpreting that. What percent of Tiger's drives travel between 305 and 325 yards? Now, what you would start with, and you don't need to write this part down though, if you were going to say state, we would go ahead and state the context of a problem. We would say let x equal the distance in which Tiger Woods hits the golf ball and how far it travels. We'd be done with that. Then we'd go to plan. And our plan would be to show the distribution and how we wanted to tackle it. So this is what you would want to do. And you're first going to start with the real life scenario. Here is the picture of the normal distribution. We have the x value right here labeled as the mean given above. And then we've tick marked on here they've done 4 distributions to the right and 4 to the left by just adding and subtracting the 8 accordingly. Then what they're going to do is take the 2 distances we want to find, which is the 305 and the 325, and standardize the data so that we can use it in the standard normal curve. Just take your piece of data minus our mean over the standard deviation. Now what they're showing you here is this is the first z-score here to the far right of 2.63. They are finding the value at that is 0.9957. Then they're looking up this particular z-score in the table, and they're finding that that area is 0.5517. And then from there, they are just subtracting out the 2 numbers to find this particular area. So then you would show your work for that portion, and that would be your do. And then you would conclude by answering in context by saying just what they've done here. About 44% of Tiger's drives travel between 305 and 325 yards, and you would be done. So let me show you an example here in the note packet, the Wimbledon example. We'll kind of talk through how to solve this problem, and then on the next slide I'm going to show you the complete state, plan, do, and conclude write-up is how you'd want to do it. In the 2008 Wimbledon tennis tournament, Rafael Nadal averaged 115 miles per hour on his first serves. Assume that the distribution of his serve speed is normal with a mean of 115 miles an hour and a standard deviation of 6. Again, we have to know or make this assumption that it's normal, otherwise we cannot use this method. A, about what proportion of his first serves would you expect to exceed 120 miles an hour? So to set this one up, I think it's easier just to start with the problem in the terms of the picture. So draw your standard normal curve, put the mean there of 115, and again, you're going to go out 6 for the first deviation, 12, and then 18, and make your marks and go both directions. Now add it to the picture. Technically, you should label this and say it's the speed of Raphael's serves is what the axis is. And then what we're trying to find is when they exceed 120 miles an hour, as you see here. So we're trying to find the proportion such that when the x is his speed is greater than 120 miles per hour. Now what they've done here is you're going to convert that to a z-score. So then you're going to come on in, do your z-score conversion, and get that the z-score is 0.83. So really we want to find the proportion such that the z-score is greater than 0.83. And then we would go ahead and use the table, go and look up 0.83. When we do that, we're going to get all the values from here all the way back. So this entire white space is going to be 0.7967. Therefore, we can back into the blue space, just showing a little bit of work here. And our answer is going to be 0.2033. So we know about 20.33% of Raphael serves are going to be faster than 120 miles an hour. That's how you'd solve the scenario. Now, let's say I just want to check on the calculator. Let me show you how to do that again. We talked about it yesterday. You're going to go on your graphing calculator and choose second vars, move over to the distribution, choose the normal CDF. You do not want the normal PDF. The PDF is going to actually give you the exact percentile. This one will give you the area under the curve, which is what we want, under the density curve, which is what we want. And remember, we're going to put the lower limit, upper limit, the mean, and then the standard deviation. So what we would type here is first the lower bound, then the upper bound, then the mean and standard deviation. So the lower bound on here is actually the 0.83. The upper bound goes on towards positive infinity, so you could just type a really big number. That should be sufficient. And then we're at mu, or the mean is 0, standard deviation is 1. In the new operating system, you would just type it in like that as a vertical list. And then you hit enter, and you should get the correct answer. So you can just check your answer that way. Now, if you're going to do this for the write-up in homework or in a free response question, here's what you would say. You could say, state, let x equal the speed of Nadal's first serve. The variable x has a normal distribution with, this should say, the mu is equal to 115, and the standard deviation, or sigma, is equal to 6. We want the proportion of serves with x greater than 120. Then our plan, basically this is going to be the work that we showed on the previous slide. The figure below shows the distribution with the area of the shaded interest. And we should label this, that this is the speed of Nadal's serves. Okay. And then what we're going to do, we're going to standardize, use table A, look up a z-score of 0.83, shows us the area less than z equal to 0.83 is equal to this, is what we said. This means that the area to the right of z is equal to, of z equal to 0.83 is 1 minus that, which is what we said. Make your conclusion, and we could say about 20% of Null's first serves will travel more than 120 miles an hour. Let's just look at another example here. Part B, what percent of Rafael Nadal's first serves are between 100 and 110 miles an hour? Let's do our kind of do portion here on the slide. This is our plan and our do. And the next slide, again, I'll put the final conclusion in the whole state plan, do, conclude format. So we have here, again, sketch of the normal distribution, and this is the scenario we're looking at now. We are going to have to get those z-scores. Just show you where this one came from here, right? We're going to take 100 minus, his mean was 115 over 6, and that's going to give us a negative 2.34 z-score, or 2.5, sorry. Now to solve this, we could do a variety of things. If we look up negative 2.5 in the table, it's going to give us this area. Okay. Then what we can do is go ahead and look up the negative 0.83 in the table, and that's just using the second one, is going to give us this area. What you could do is just subtract those two numbers, and when you do that, you're going to get that the blue shaded area is 0.1971. Now let me again just check that on the calculator and type in this. And when you do type this in right here, it will confirm for you that you have the right area. Now let's look at the state, plan, do, and conclude for this problem. Again, our state is going to be the same thing. I just need to fix this. Our symbols got lost. That mu is 115, standard deviation is 6. This time we want the proportion of first serves with x in between 10 and 110. Our figure below shows us the distribution with the area of interest. Again, I should label this the speed of Nadal's serves. First serve, I should say. To do, we're going to standardize. So when x is 100 and when x is 110. And then we're going to show the work of getting the z-scores that we need. Then we're going to use table A and look up our z-scores. And then this is basically what we came up with is, as we said here, we're going to subtract the two z-scores and get what we need to. We can conclude by saying about 20% of Nadal's first serves will travel between 100 and 110 miles an hour. This is a great way of putting the answer in context. This is a good problem to take a listen to. This is kind of a backwards one. So let me show you how you could approach doing this. According to the CDC, the heights of 3-year-old females are approximately normally distributed with a mean of 94.5 centimeters and a standard deviation of 4 centimeters. What is the third quartile of this distribution? So this one here, they want to know, what is the number we're looking for on this graph? We know a third quartile. Third quartile is roughly the 75th percent. So what we need to find is at what tick mark on this axis will we cover 75% of the graph. So what we need to do is go to the table, go to table A, and go backwards. We want to look in the table and find where we can see 0.75, maybe 00. You're going to find that this happens in between 0.67 and 0.68. The z-score of 0.68 has an area above 0.75 by just a little bit. This z-score has an area just below 0.75, so that's the z-score we have to do. So we found the z-score. Now we're going to have to unstandardize our information. So we're going to use the z-score formula, plug in the z-score that we found. I don't know the piece of data. I do know the mean here. And I know the standard deviation. And if you solve this algebraically by multiplying by 4 on both sides, and then adding 94.5, we're going to get that x is 97.18. And if you look at the picture here, what that's saying is this is where about 97.18 centimeters would fall. So anyone lower, shorter than 97.1 centimeters, all of those people roughly make up 75% of the data here. Now let's look and see how you would put that in a state, plan, do, or conclude 4-step process. This right here is a nice way to put it together. In this case, state our variable. Let x equal the height of a randomly selected 3-year-old female. Be specific enough. The variable has a normal distribution listed in this format. Perfect, that's all we have to say. The third quartile is the value is 75% of the distribution to its left. This is being very specific. So we just put that now in a picture in the plan section. The picture illustrates what we're trying to find. Again, we should put here the heights of the 3-year-old females and put that in centimeters as a label for our graph. And then we're going to use the table, find the area closest to this, which is this right here. State that you're finding this 4-digit number in the table, corresponds to the z-score. Then we're going to unstandardize, and when we do, we get that x is 97.81. Now put the conclusion in context. The third quartile of 3-year-old female heights is 97.18 centimeters. Now I've done a sample of the various types of problems. If you want to hear some more examples, I'm going to go through some of the ones on the fuel efficiency example. Other than that, it's really nothing new. They're just different variations. And if you were asked to solve these in homework, you would want to do the state plan, do a conclude process for all of them. For our purposes for notes here, I'm just going to show you how to go about the doing and the plan portion. So the first scenario is here. Suppose a model describes the fuel efficiency of cars currently registered in your state. So that's our in context, by the way. The mean is 24 miles per gallon. Standard deviation is 6 miles per gallon. What percent of all cars get less than 15 miles per gallon? We've done this problem already, so let's refer to the standard normal curve and get it set up. So the sketch of our scenario would be the percent of all cars that get less than 15 miles per gallon. So they want us to find the percent where x is less than 15. Now we need to standardize that, so let's compute the z-score. 15 minus our mean over our standard deviation. So therefore we're finding a z-score of a negative 0.5. So we could restate this as we really want the percent of the z-score is less than negative 0.5. So we have our plan. Let's do it. Go into the table, look at negative 0.5. And when you look that up, you're going to get 0.3085. You can also check on the calculator by doing that. Use a lower bound of something like negative 9999. An upper bound is going to be negative 0.5, and you could do that portion. Let's take a look at part E. What percent of cars get between 20 and 30 miles per gallon? So let's set up the scenario for that. So we're going to do our sketch of that scenario, and then what we're trying to find is the percent or proportion that the x is in between 20 and 30. We can convert that to a z-score. I actually already know, by the way, that the z-score of 30, it's 1 standard deviation. That z-score is going to be 1. The z-score of 20, we can compute that. And let's just do that here real quickly. So 20 minus our 24 over 6. We're going to have a negative 2/3 with that, or a negative 0.67 is our z-score. And then we can go ahead and find the area. Now, what I'm going to do is, I do recall that 1 standard deviation away, the area under this, 1 standard deviation on both sides is 0.68. I'm just going to cut that in half. So let's cut that in half, which tells me this area has to be a 0.34. To find the one at the negative 0.67, what I'm going to do, I'm going to look up the in the table to get this value here. Then I'm going to subtract it from 0.5, and that'll end up giving me this here. So let's do that. It's going to be 0.2514, and then if we take 0.5 minus that, we'll get the red area, which will give us a 0.2486. So then for this problem, we're just going to add together the 0.2486 plus the 0.34, and we're going to get that the area is 0.5886. Now I'm going to try putting this in the calculator, not in a standardized method to check the answer. What I'm going to do this time is go back and still do the norm CDF, so let's do that. But this time I'm going to type in the actual values for X, not the standardized. And it's right up here at the top of the page. I fit it in. If you type in your lower bound of 20, your upper bound of 30, and then the actual mean and standard deviation, you will find that the calculator will confirm our answer within reasonability of rounding. The calculator gave me 0.5888. Be careful, you need to show the work on where this is coming from, that this is it. So the calculator is more of a check. Again, read the caution here from the AP. Students often do not get full credit because they use calculator speak to show their work on normal calculations. They expect you to have the due portion involve this math, so you do need to understand the logic behind it. Let me just set up one more of these, and that should be sufficient. So let's set up the scenario here. Okay, they want us here to describe the fuel efficiency of the worst 20% cars. So 20% cars, again, we know if we cut down the middle, this is 50% to the left. So I'm going to just estimate maybe the 20% of the cars is going to be right in here. So that's the bottom 20% of the cars. So what we have to do for this one is a reverse. I'm going to go to the table A, and try to find what z-score is closest goes with 0.2. I have to actually go to the negative z-scores, and we're going to find that we have to use that it's going to be closest to negative 0.85. The area for that z-score, by the way, comes back to 0.1977. The next closest is going to be at 0.2005. That's for the z-score of negative 0.84, and that exceeds it by the 5 here, so that's not good. And clearly you can tell my picture's not great, so I'm going to actually fix my picture if this is the real AP exam. A z-score of that is going to have to be somewhere in here. Okay, so I was just a little bit off, actually quite a bit off on that one. Now we're going to have to unstandardize, so we're going to put our z-score as this, equal to our piece of data, minus our mean of 24, standard deviation, and then solve it. The answer to this is going to be X is equal to 18.9, and that would be miles per gallon. Which, do a gut test, does it go between 18 and 24? Yes, I am correct. Now let me show you one last thing. You can actually do a calculator check on your inverse calculations, and you're going to be looking for inverse norm. Let me show you how to get there. Here again, you're going to do your second vars, and under the distribution, you're going to see INV norm. This will allow you to check, and what you do for this one is you're going to put in here, it's 3 things. You're going to put the percentile, the mean, and then the standard deviation. So the percentile, the mean, and standard deviation. So for this case, I should be able to put 0.20. Our mean was 24. Standard deviation was 6 to check the answer. And when I do that, the calculator actually gives me an answer of 18.95. If you have more questions about these problems, just seek me out for help or ask a friend. Other than that, I think this should be a sufficient amount of examples. Now, just remember your calculator shortcuts here, though. To get to the 2, it's second vars distribute. If you want to find the area under the curve, use normal CFD, put the lower bound, the upper bound, mu, and standard deviation. You can keep these in terms of the actual data you're using, your X values that would work, or you could convert the lower and upper bounds to z-scores. If you do that, you would use the mean of 0 and the standard deviation of 1, so be careful. The other thing you can do is find the percentile you're at, given the area under the curve. Use the inverse norm, type in the percentile, the mean, and the standard deviation, and you can just use basically the given data set for that example.